All right, there we go. So we were predicting the signs of this delta S and these reactions. We saw here where we went from a solid and a liquid. We went from 2 moles of material down to 1. So we would expect that our entropy would be less here. Here we were going from a solid where we had 1 mole here. We're going to 2 moles, and one of those moles is going into a gas. So that's definitely a positive delta S. Okay, so that's the kind of thing that we were looking at yesterday. I do remember going through this slide, so if you want a further recap of this, you can go back to yesterday's video. To be able to work with these and determine a change in entropy in a reaction, you're going to be looking at the sum of the absolute values of the entropies of the reactants and the absolute value of the entropies of the products. Okay. You also have to multiply those entropies by the mole values from the stoichiometry in from the coefficients in the equations. Okay. So for example, if we had this reaction going on here, we've got our nitrogen, we've got our hydrogen, and we have our ammonia here that we're creating. They would give you a chart with the values. Okay. The chart typically is at 298 degrees. Or 298 Kelvin, excuse me. There's no degrees in Kelvin land. And remember that these entropies on those charts are going to be given in joules, okay? And that becomes important when we get to our next section, which is on Gibbs free energy, because there we're going to be working with our enthalpy values, which are in kilojoules per mole. So you have to convert this into kilojoules per mole to make them work together, okay? All right. When we do that, again, they're going to give you the values. So this is the value for the ammonia. You would have to multiply that by a 2 because there's a 2 here. So this is your products, and then you're going to subtract the values from your reactants here. So here we have 192. That 192 is your nitrogen. You only had 1 of those, so they're not multiplying it by anything. And then they're going to take the 190 or 131 for the hydrogen and multiply that by 3, add those values together, and then subtract this value from this value, and you get your negative 199. Okay? So if this value is a negative, then that means that our entropy has decreased. And again, that makes sense because we've gone from 4 moles here down to 2 moles. Okay. So that's that. I want to switch over here and talk real quick about this. So on your in your materials for today, you're going to this is for, so I'm going to try to get through Gibbs today. If I don't, I'll finish it tomorrow. It won't take long because it's not going to be that much longer. And then you've got 3 worksheets that you're going to work on. Okay. I can run these off for you if you want, but I'm not going to be able to probably do it this hour. I can get them to you 7th hour. You can pop back at the end of 7th hour, beginning of 8th, like you did that one day, I think you guys did. Yeah. But I can run these off. I just haven't gotten around to it. But this has some good information on it. So about entropy, it kind of talks about it in a little different way than I did yesterday. It talks about entropy, so in actual, when particles or energy in the system are more spread out into the microstates, we say that the system is more disorder or entropy. If the products or the energy in the system are less spread out, then that would be less entropy. That makes sense, right? And then where did they say it up here? It was really good the way they worded it. Oh, here it is. So entropy can be thought of as a measure of the energy lost to molecular disorder or randomness in a sample. So that's kind of like, you know, we're disorganized, and you know how when you're disorganized you can't find stuff, and so you know you can't get as much work done because you're disorganized. That's kind of the idea here, okay? Because of this disorder, they don't have as much energy to be able to actually, do whatever it is that the molecules are trying to do, okay? And the more disorder they have, the less effective this stuff is, right? So, but I just thought that statement in these notes, I thought was very, very pertinent to what we're talking about. And I really liked that idea. So go through and kind of read their take on some of this stuff. I think that they do a really good job on it. I did include the answer key as well, but I want you to go through and do the work first and then go back and check your answer key and see how things meshed out. If you did this earlier and you got into this earlier, there was an error here that I've now fixed. I re-uploaded this to Google Classroom, but if you looked at an earlier version of it, this one, there was an error on here. So, all right. So now we're going to be talking about this idea of spontaneity or thermodynamically favorable. So if you watched yesterday's discussion, I talked in there about how they, on the AP exam, they do not really like you using the word spontaneous, okay? Most people out of chemistry land think of spontaneous as boom, it happened, okay? In chemistry land, spontaneous doesn't mean boom, it happens. It means boom, it's going to happen sometime, and we're not going to have to put any extra work in to make it happen. Okay, we don't have to put any extra effort into it. Like the rust on my bumper, okay? Luckily, it's not boom, it happens. It's taken 10 years. It's starting to happen now, But that is a spontaneous reaction because nothing had to be added in to make that happen. It just happens over time, okay? So that reaction is considered thermodynamically favorable. And that's what they like you to use instead of the word spontaneous. So do not write down spontaneous on the AP exam. It will get marked wrong because they don't like it. You want to use the buzzwords they like to hear. And they like to hear thermodynamically favorable. All right, now, the equation that I showed you back here, that is on your sheet. So I think it's on, yeah, that one's on here. So you don't have to memorize that one. And this one is on there as well. You just need to know how to use it. Okay? So this is called Gibbs free energy. And when you get done with this calculation, what you are looking for is this value negative? If it's negative, then it's going to be thermodynamically favorable. It will occur without any extra outside intervention. If it is positive, then you're going to have to add in something. You're going to have to do something to make it work. Okay? Got to change the temperature, which will change this value. You have to change something in that system to make it happen. And we're going to talk about that in terms of like electroplating when we get into the end of this unit, because there are ways that can happen. You just have to put extra energy in to make it work. All right, so entropy and spontaneity, again, delta G is going to represent the change in that free energy for a reaction. It's going to be that driving force and how much energy is available to do work versus getting lost in that molecular disorder. Okay? So these prime here, what that means is that that's at standard conditions. And standard conditions are 1 molar, 1 atmosphere pressure, and 298 Kelvin, which is 25 degrees Celsius. So they kind of consider this, this is like, what we're sitting in right now, okay? As opposed to much lower than this during the winter in this room, but it's at least become comfortable. Now, you have to be careful with these units. Like I was saying before, and I said in yesterday's discussion, I showed you the Appendix C that I gave you a copy of a while back when we were doing the delta H changes. Your delta H is in kilojoules per mole. Your delta S is in joules per mole. So you will get oftentimes figures like 327 or something here. This is going to be, let's say that we ended up with 952, but that's going to be joules per mole. You have to move that decimal point 3 spots over to make it work. So get that into like they will get you with this. I guarantee it. If you are not careful, this is the common place that people slip up. So be very careful with that. Okay, so like I said, in order for the equation, all the units and products in the mixture must be present in their standard. So we have to have 1 ATM, 1 molar, and it has to be at 298. Again, this is that joules versus kilojoules that we were talking about. And in order for thermodynamically favorable reactions, they have a value for delta G that's negative, and a negative delta G is favored by a negative H and a positive S. And we're going to talk about that in just a second. This was back in the day where we had big ideas. We'll talk about that in a minute. If a thermodynamically favored reaction may still be very slow, one of the energy of activation is high. So the reaction has a negative. We just need to talk about this. Okay. I also, so this is in your thing, but when I was going through these sheets, the way they have this presented in these sheets, I got to thinking about this. Okay. So the way she has this listed here, this is the same order that it is in that Gibbs free equation on your sheet. Okay. So your Gibbs free equation has, are you going to let me, you're not going to let me write on here, are you, stinker? Why can't things just work? Why can't things just work?
Can I get your autograph 3 times?
Absolutely. I was supposed to have done it for that kid that I just gave it to Monty for, wasn't I? Yes, I did. Is that one yours? Yes, he is. You need the date too, or?
Yeah.
No? Okay.
And that one's yours?
Yep, that one's mine. Yep.
And that one?
Yes, that one is mine as well.
All right. I thought they were.
I'm sorry.
We're getting there. Thank you.
I'm sorry. I've tried to ask, and a couple of the classes I got so.
Well,
I was teaching IMFs, and that's one of my favorite subjects.
These are the 4 that we have out of like 150.
Yeah, I heard. Yeah, we heard Monty calling everybody down. So. Okay. All right. So like I was saying, if you look at that Gibbs free energy equation, this is listed first, this is listed second. Okay. And if you just remember, zeros are here. Now think of this. Okay. This is everything. It's coming together. Do you see that? It's hugging. It's bringing everything in, right? You know me and my hand motions. Okay. So at all temperatures, everywhere, everything, right? So when they look like that, then this is going to work. Delta G is going to be favored. Okay. Here, they're excluding everything. Nothing is going to work. Get out of here. Okay. So if you can draw this and think about these arrows that way, like nothing's getting in here. Nothing. Okay. And then here, if you go this way really fast, that's high. And if you go this way, that would be low. So you can kind of think about it in terms of these arrows, because what they're doing is they're showing you the state of the arrows here. Then that's going to tell you what these things would be. Does that make sense? Kind of the way that you can kind of remember these to make it work. Because you need to memorize this chart. Like if you're taking, like even for my class, like either way, but especially for the AP exam, you've got to memorize this chart. So that's an easy way to do it. You just use their equation And you think of, oh, everything, all temperatures, no temperatures, high, low, you know, and then it kind of works out. Whatever you got to do, just get it memorized. I don't care. I'm just trying to give you a way to kind of wrap your brain around it. Okay. When I print this off for you, these highlights are not going to show up. Just so you're aware of that. These documents are loaded on there, so you can go back and highlight it with a highlighter, but it's not going to show up. Okay. But that helped me. The other thing that I've done is, what did I do? So P and N, okay, always positive, so that would never run. So pun, none, okay, because it's not going to run. Pun, no run, whatever you got to remember. And then this was N and P, and then it would always be good. So naps are good. So however you need, but then you got to figure out these. So that's why I like the arrows, because then that helps. So, but whatever you got to do to make it happen. The other thing that you can do for these is I think of ice. Okay. So if my temperature is low, okay, if I have a low temperature and my disorder, that would lower my disorder too. That ice would form in low temperatures, but it wouldn't here. It wouldn't form at high temperatures. Okay, does that make sense? So I think I kind of think of it in terms of, so I can kind of reason through it this way. And then here, if I was thinking of ice here, this is going to be high temperatures and high disorder, okay? So this would be like my gas at this point. So a gas would form here, because a gas would be at high temperatures and it would be at high disorder. And that would happen at high temperature, because remember delta G is when it happens. So a gas would form at high temperatures, but it wouldn't form at low temperatures. So that's the way I can also reason through some of this. Okay. So however you've got to get this chart memorized, I don't care. Just get it done. Okay. All right. You can also do Gibbs free energy if they give you the Gibbs values for the products and the Gibbs values for the reactants. And that's done the same way that we did it for enthalpy. It's done the same way for entropy. You just have to multiply it by the coefficients in the equation. Okay. Again, positive delta G, no reaction. Negative delta G, it is. Okay. Now, think about that though. If it's not thermodynamically favored one way, okay, then if you reverse the reaction, that one will be. So whichever way is it thermodynamically favored, the reverse of that reaction is going to be thermodynamically favored. Okay. All right, reaction with a positive delta G can be forced. Again, we can make this happen, okay? We can make electricity. Oh, that looks like a heart rate or something, doesn't it? We can use electricity, like for electrolysis, where they're splitting water up into hydrogen and oxygen. We also use it, they use electricity like in electroplating. So a lot of your costume jewelry and stuff that you'll get, it's metal, like some cheap metal, a lot of times nickel or something like that. And then they'll electroplate it with a more precious metal like gold over top of it, or silver or something like that. But it's just a thin layer. And they force that to happen by using electricity. So that would be another example of where this happens. Light to overcome endothermic ionization or photosynthesis, for example. Okay, we know photosynthesis happens. All right, you have to use a delta G. There has to be some stuff going on in there. So, all right, let's see, thermocoupling. You guys can get into that, like more in physics and stuff. Cellular reaction biochemistry, these phosphate groups to the glucose. Oh gosh, I hated doing all of that stuff back when I had to teach bio. So that's another one. If you get into AP bio, they go into a lot of that stuff. ATP, ugh. Oh God. ATP to ADP, again, painful. And then when we look at this, we're looking at stuff in terms of Le Chatelier, and we'll get into that. I don't think I'm ready for that today. No. So we'll get into that. I want to, so yeah, we did get through this. I might actually have time to run this stuff off for you guys. Yeah, I probably will. So what I want you to do then, I'm going to go and run these off real quick. And then once I get these run off, I'm going to have you work on this stuff. Okay. So just give me a minute to do that. And I'm going to stop the meeting then. So let me stop this. And, oh, we should do some, maybe we should do a couple sample problems on this. Maybe that's what I should do. We didn't do any sample problems with Gibbs free energy, did we? That one would be easy for you guys to do. I wanted to do here. I don't have any sample problems for these guys. Failed you once again. I know you're used to that, aren't you? Just like, oh, Lippy, not again. I thought I had some sample problems on there. Why don't I have those? That would have been big idea 5 that year. Is there any on this? It's enthalpy change. It's all enthalpies. We've done that before. Further in than this. The first year I taught this stuff when I really didn't have a clue what I was doing. Oh, I'm used to my afternoon nap, you guys. This is my afternoon nap. It's that appendix that I need. Anybody need a new copy of the appendix? Still got it? Okay. I'm waiting for this thing to open up over here. I just have the spinning wheel of death. Here we go. Sorry. We got any. trying to see if I had, these are still just enthalpy. Ugh. Can't I find what I want when I want it? Sorry. There. It says answer key. Let's see. Okay, here is some entropy at least. These are all delta S. Yep, I still don't have it. I'm sorry. Well, they've got lots of examples on that sheet. Let me just get those sheets run off, and then we'll try to do a couple problems out of that, okay? Oops, that's the key. We don't want that. We want the actual sheet. I do have the keys loaded for you, though, so you can access the keys. Print on both sides. We don't want to do that, I don't think, because there's some that aren't full pages. So one copy of that. File, open. File, print. And this one, here we go. Okay, so then print. And yep, this was the one that I didn't have. So then I get charged for an extra page if I do it back to back to back to back. Yeah, because I'm cheap. All right, I will go and get those run off for you real quick.
Will there be a video to watch tomorrow?
Probably not. I'm probably just going to have a work day on these worksheets, and I can